like to me that it's always concave down, doesn't it? It's concave down here, cup down here, and it's cup down here, right? So I thought it was all concave down, but it's not actually. It has kind of like Dirk van der Klein's little slight bumps. It does something like this, and I didn't catch it in the graph. So that's good. That's good that I found that, but I went and did the same thing as I did in the other one, and this is without steps. So this is without all the gory details, and you'll see how easy it is. So the first thing is I said, okay, look, 0 and 2.52 looks kind of like an important point. I clicked it on Desmos, and I got that point value. And then, do you see other points that might look important? Right, this one, -2, 0, and this one over here, 2, 0. They're minima, so they look important. They look critical. So they're critical points. So here's my arrows going down before -2. That also tells you that there's a change in direction, that this is a critical point, because he's going to change directions in between those two. And it changes direction, right? It's like the roller coaster thing. Goes up, flattens right at the top, and goes down, and then I have it going up again. I didn't understand what local max was, or they call it relative max, when I was taking Calc 1. What it means, it's a bump, and those bumps are actually really important. Like, for example, you could have, I know that in Denmark, like in the United States, our body mass index prevalence has steadily gone up. But in Denmark, they had it go up for a while, and then they had it go down for a while, and then they had it go up again. So that bump, they're asking me about that bump. Why was there a bump? What happened to that bump? So those bumps make you ask questions. There's something up, something's different here. And so it's not the absolute max, because the little wings on the side keep going up forever. But it is a bump that's kind of, must be something going on there. So we call those a relative max. It's relative to everything else around it, or a local max. That's what I thought when I saw this. I thought it was concave down, concave down, concave down. I was wrong. You're going to see that. The analytics caught it, which I just advocated I'd get rid of. All right, so we're done. I have the slope graph, I have the concavity graph, I have all of it. So this is what I thought was a slope graph. Isn't that it? Down, up, down, up. And that's supposedly my concavity graph, which is not going to be correct. That's what I saw. That's what my eyes saw. Your eyes see it too? It looks like that, right? Okay, so here's the analytics. The analytics are a doozy, but I left off all the steps, so you can watch it all come out and play out. The derivative, it's a fun one. Chain rule. Actually, this is the best rule in the class. Everybody does chain rule the best, which is very unusual. Power rule is something we need to work on. So this is chain rule. This is what the derivative looks like. And just as a tip, always write your thing in positive exponents, because you got to do stuff with it. You have to take the second derivative of this thing. So if you have it in negative exponent, it's a little bit more messy to work with. And you have to do plugging in, and you have to do evaluating of numbers in there. So it's good to have it written out in positive exponents. So that's what it looks like after I take the derivative. Recopied out there if you're taking notes. It's at the top again. Where does y prime equal 0? Well, y prime is a fraction. And the only way a fraction can be 0 is if the top is 0. So I set the top equal to 0. I've totally left the bottom off. And the only way for this fraction to be 0 is if x is 0. Can you see that by direct inspection? You can actually write it down. You plug in x equals 0 into the 2/3 times 2x. 0. Right. So x is 0 is 1 point. I got to get the y value, and I messed up the y value. It's actually 2.53, but I knew that. You know, that's how I caught myself. Like, I got this value, and it was totally wrong. I was just, I don't know, I made up totally numbers, but I knew that this value was 2.53 because I saw it on Desmos. So it's not 0.4, it's actually 0. Let me copy this. 0, 2.53. So there's another place you can get critical points, and that's if the denominator is 0. And so in addition to step 8 from the previous section is that you set the denominator equal to 0. And that's where you get your x equals plus and minus 2. Recall that there was like those little spikes down at x equals minus 2 and x equals 2. This is how you catch those spikes. And this is a difference of squares, which you'll never see in a real life problem. I've never had anything where it was a difference of squares, but let's pretend it'll happen. So far, so good? Y values are easy, as they should be. I know that I'm right because I saw it on decimals already. So negative 2, 0 is one critical point, 2, 0 is the other one, and 0, 2.53 was the third one. Okay, so far, so good? Then you take all those critical points and you lay them out on the slope chart, and you choose values in between those in a table. So you choose a value to the left of minus 2, choose a value between minus 2 and 0, choose a value. It's a real pain in the butt, this thing. 0 to 2, you choose another one, and that one after 2. And so I chose minus 1,000 because I'm hoping to be lazy and just see the answer without doing things. I chose minus 1 and 1 because those seem to be the only nice numbers in between those two regions. And then I chose 1,000. And I went and tried 1,000 first. And if you put 1,000 into this formula here, the top is positive, 1,000 is huge. It's positive, the whole thing's positive. So I know the answer is positive there. But if I put minus 1,000 in, how's that going to change that answer? Top is negative and the rest of it's fine. So it's, I can see the answer from this one, from the bottom one, I can see the answer to this one. The only difference between this and this is going to be negative. And then these two I actually had to plug in numbers and see, and it turned out I got the number, and one is positive, one is negative. So now I have the slope chart. It was negative first, then positive, then negative, then positive. And voila, our little W curve starts showing up. You see the curve from the beginning from decimals starting to show up? It's pretty incredible, actually, that mathematicians had to do this. I mean, there was no choice. There was nowhere to go. If you look at the first models of the weather that was developed by Edward Lorenz, he coded it in Fortran. That means he had to do punch cards, take those punch cards to some lady. She would have a list of punch cards from everybody. She'd run the code. He didn't have any bugs in it. They told me that they didn't have bugs because they were very, very careful in the first time round, because if you made a mistake, you had to do it all over again. And then the lady gave him all the data, the output, and then he had to plot it by hand. So the idea that you can't predict weather, Edward Lorenz published that. His plots are made by hand. He plotted all those points by hand and drew it nicely on a graph. Maybe their handwriting was better back then, because they had to do that all the time. Okay, that's what my slope chart looks like. And oh my goodness, look at the second derivative. It's quotient rule. And then with the quotient rule, I had to, did I not square the bottom? I just need to square the bottom. Okay, so don't forget to square the bottom. It doesn't matter because I went straight to Maple, and I just told it to simplify it. I guess Mathway does that, right? You can stick it in there to simplify it. You can simplify it by hand. I did all those things when I was younger. You should do them by hand and just know that you have to simplify some of these things. It turns out to be x squared minus 12. The next step is to set the second derivative equal to 0. And I get something around 3.64. This did not show on decimals, so I did not see this. And I have to do the same chart thing that I did for the y prime. So I chose numbers in between all the three, and I have to plug them back into the y double prime. And I got positive, negative, positive. So the area that I'm looking at on decimals, it was all concave down. But the area right outside of that, it must have been concave up. and I just missed it. And I just checked, I drew the graph of the second derivative, and you can see it's underneath the x-axis, right where it says that I just double checked it by looking at the graph of the second derivative. I got the y values at those points. These are inflection points. They're actually important points. And the y values are 4.4. And so this is what that curve actually looks like. Remember the two important charts are the slope chart. From these two pieces of information, you recreate the graph. You label, you first plot all your important points, the minimum, these 2 points, the maximum, the local max, and the inflection points. They get plotted first, and then you make it do this, and you make it do this. It changes concavity from concave up to concave down, right at that inflection point at the top, right up here. And so I forced it to do that. So concave up, then concave down. Then it goes down and up, and then down and up again, and then it does another concave down to concave up. I guess this is supposed to be up, not down. And so that's it. I mean, that's what you're supposed to do. It's a bear. It's tedious. So